You know, when you look at a single drop of pond water, what do you really see? Probably not much, right? But what if I told you there's an entire bustling universe hidden inside it? A world full of tiny creatures totally invisible to us. So how on earth do we peek into that hidden world? Well, that's exactly what we're going to break down in this explainer. We're going to pop the hood on one of the most important tools in all of science, the compound microscope. We'll figure out exactly how this incredible piece of tech takes something impossibly small and makes it big enough for us to actually see. So here's our game plan. First, we'll look at why a simple magnifying glass just doesn't cut it for this job. Then, we'll get into the brilliant two-lens solution. After that, we'll trace the exact path light takes through the whole system. And finally, we'll dive into the surprisingly simple math that gives the microscope its amazing power. Let's get into it.
All right, first things first. You might be wondering, why can't we just use a really powerful magnifying glass? And that's a great question. It turns out there's a hard limit to what one single lens can do. Yeah, a single lens can only bend light so much. You pretty much hit a wall at around 9 times magnification. Now, that's great if you're reading some tiny fine print, but to see something like a single cell or a bacterium? No way. It's not even close. To get into their world, we need a whole new approach.
And that brings us to the genius solution, the compound microscope. The secret is right there in the name, compound. It completely shatters that single lens limit by combining the power of 2 lenses working together as a team.
So, meet our power couple. First, you have the objective lens. This one sits right up close and personal with the specimen, and it does the first round of magnification. Then, you've got the eyepiece. That's the part you look through. And here's the really slick part. The eyepiece is basically a magnifying glass for the already magnified image from the objective. It's like magnifying a magnification, just a brilliant 2-step system. Okay, so we know it's a 2-step process, but how does it actually work? To really get it, we're going to follow a beam of light on its journey, all the way from the specimen, through both lenses, and straight to your eye. This is where the magic really happens.
First stop is the objective lens. Its job is to collect light from our tiny object, which we're calling AB here, and focus it. This creates a first image inside the microscope tube, which we'll call A', B'. This image is real, which just means it's a point where the light rays physically cross. It's also bigger, and, this is important, it's inverted, or totally upside down.
This diagram shows that first step perfectly. Follow the rays of light coming from the object AB on the far left. As they pass through that objective lens, they get bent and come together to form that first, bigger, upside-down image, A', B'. Okay, so now that image becomes the object for our second lens.
Now let's bring in the eyepiece. The eyepiece takes that real image we just made, A', B', and treats it as its own object. It then acts just like a regular magnifying glass, blowing up that image even more, to create the final image we actually get to see. We'll call that last one A', B'. Looking back at our diagram, you can now follow the light from that middle image, A', B', as it travels through the eyepiece on the right. Notice how the light rays spreading out from the eyepiece don't actually cross? Instead, our brain traces them backward to a point where they seem to come from. That's what we call a virtual image. It appears way bigger, farther away, and that's what we see.
So, to sum it all up, the image you finally see has 3 key features. 1, it's virtual, like we just saw. 2, it is of course hugely enlarged thanks to that 2-step process. And 3, it's still inverted compared to the original object. So yeah, if you move the slide to the right, the image you see actually moves to the left. It takes some getting used to. Okay, we know the image is bigger, but how much bigger are we talking? That's where a little bit of math comes in. And don't worry, it's pretty simple. Let's break down the formulas that control the microscope's real power.
The total magnification is surprisingly easy to figure out. It's just the magnification of the objective lens multiplied by the magnification of the eyepiece. Each lens plays its part, and their powers combine to give you that final massive number.
Let's break that down, starting with the objective. Its magnification, which we call m sub o, is simply the length of the microscope tube, L, divided by the objective's focal length, f sub o. All that means is a longer tube or a shorter focal length gives you a more powerful objective lens.
Next up, the eyepiece. Its magnification, m sub e, is found by dividing d, that's the standard near point for the human eye, around 25 centimeters, by the eyepiece's focal length, f sub e. And just like before, a shorter focal length means more magnifying power.
And when we put it all together, we get the whole shebang. Total magnification equals the tube length over the objective's focal length times the near-point distance over the eyepiece's focal length. The big takeaway? To get insanely high magnification, microscope designers use lenses with very, very short focal lengths.
Theory is one thing, but let's see what these numbers look like in the real world. We'll take a typical example and just run the calculation to see the kind of power we're really talking about here.
Here's our setup. We've got an objective with a 1 centimeter focal length, an eyepiece with a 2 centimeter focal length, and a 20 centimeter tube. So, what's the total magnification?
Let's just walk through it. First, we plug our numbers into that formula we just learned. The objective's magnification is the tube length, 20, divided by its focal length, 1, so that's 20. The eyepiece's magnification is the near point, 25, divided by its focal length, 2. That gives us 20 times 12.5.
And what's the result?
A whopping 250 times magnification. Just like that, our object appears 250 times larger than it actually is. That is the power of compounding two lenses. It's the difference between seeing a tiny speck and seeing the teeming world of bacteria living on that speck.
So, to wrap everything up nice and neat, let's put together a quick little cheat sheet with the key formulas that make all of this possible.
And here it is, all in one place. The objective's power comes from the tube length and its focal length. The eyepiece's power comes from the near point and its focal length. And the total magnification is simply those two multiplied together. Pretty cool, right?
So there you have it. We've journeyed through the optics, traced the light, and even crunched the numbers. It's an incredibly elegant system that lets us see the invisible. We figured out the how. So I'll leave you with this question. What unseen worlds will you imagine exploring?